All right, good morning, everybody. Let's begin the second portion of the DNSI training, which focuses on the caching name server, which we call DNSI CachEServe. CachEServe is a product which shares a similar history to AuthServe in the sense that it is a single purpose, single functionality DNS server. It is a standard protocol adhering DNS server, so it has all the same interoperability features as AuthServe does. However, it does not provide capability for doing authoritative DNS. It only does recursive or caching DNS. So let's begin with an overview of the course. We will spend a very short time with introducing the DNS and where a caching server lives in the overall public internet DNS service. We spent a lot of time in the AuthServe course already looking at the architecture of typical deployments, so we won't go over that in too much more detail. However, I'll just point out a few of the properties that make caching a significantly different type of function than authoritative service. Then the rest of the class will proceed also very similarly to how we worked with AuthServe, in the sense that we will begin with a new installation on a host with CachEServe 7.7, and the approach will be to add configuration a little bit at a time in order to understand each of the configuration objects and the behaviors of the server. So we'll start with just becoming acquainted with the basic server and view functions, and you'll recognize the general configuration approach because it uses command channel and the interactive command channel client that we call NOMTEL. It's just because you're connected to a different server, the commands that you'll have offered to you that are valid, those instructions will all be appropriate to CachEServe as opposed to AuthServe. But conceptually, you will see a lot of similarity to how the configuration actually is implemented. The structure of the objects is slightly different. Of course, it's a different product, so there are no zone objects, for example. There is instead a resolver object, which is where the content for the DNS responses will come from. It is the resolver object, as opposed to AuthServe, where the zone object is the origin for the DNS responses. We'll also see that the view is a much different thing in AuthServe versus CachEServe. So that will be something we'll have to learn about. The good news, I think you will think it's good news, is that there are not a lot of databases because we're not storing content in the form of zones. There is not as great a need to have persistent storage, and so the master slave, those databases for the content of DNS resource records, those no longer appear in CacheServe. The one database that remains for CacheServe, you might guess, is the CacheServe's configuration database. In other words, the persistent storage for the settings, all the properties on the server objects and the resolver objects, and the monitoring object, which you'll remember from authserve. So there are similarities, and yet there are differences. So after a couple of exercises that acquaint us with the nature of the basic configuration elements, we'll start looking at operation of the CacheServe. Specifically, we'll reintroduce the statistics that one can obtain from the server, and we will learn how to interpret those statistics in terms of how CacheServe is using the computing resources and network resources of the host. There is a set of rate limiting policies that are different than those that we briefly looked at with authserve, and we will spend a good amount of time here. You already are familiar with the events system. Of course, the sorts of interesting activity that might occur on a caching server is different than what you see on a authoritative server. So we will just briefly look at the event system because there's another difference, and that is that there is a CacheServe has a connection object where one subscribes to the event. So there's a slight difference here. The SNMP support is exactly the same. I will not ask you to repeat the SNMP agent configuration. However, if you perhaps did not do that lab or were not successful for any reason, then you have another chance if you want to start over with the SNMP agent in CacheServe, and I can give you the name of the IP address, and you can reconfigure. And I think you already have it because you know the instructor's IP address. So you can reconfigure that, and then you can send your SNMP traps from CacheServe as well as authserve. So those of you who configured authserve's SNMP agent, I'm still watching right now. I'm looking at the activity from your authserve, so we can add the CacheServe to that as well if you want. But that's will not be a requirement. We'll spend a little bit of time talking about some of the weaknesses that are just part of the DNS protocol. I talked briefly last night at the end of our session with authserve about the DNS sec and the secure extensions. That is one way to help secure some of the DNS interactions, but there are others that remain, and we can talk about some of those vulnerabilities that are specific to a caching server, specifically around cache poisoning and the built-in defenses that CacheServe has for reducing the likelihood that an attacker can exploit these weaknesses in the protocol. We already spent a good deal of time with RTV, the query store, which we used with authserve in order to capture DNS traffic. Again, this works precisely the same way. I may spend a short amount of time just reviewing some of the analysis commands with the query store, which are particularly useful for a caching server as opposed to authoritative server. And we also can spend some time with the auth monitoring object, which is a way of capturing traffic. Instead of from the clients, we can capture traffic between CachEServe and the authoritative servers, which is a very useful mechanism for debugging problems with resolution. So we'll look at that. The real-time alerts or query thresholding, again, we will not spend any more time than we already have on looking at that. Conceptually, it is precisely the same. It's a mechanism for sending some kind of an event, either event in the sense of a command channel event or an SMP trap if the rate of queries exceeds a threshold that you set. So this will all take place just in the context of generic DNS resolution. After that, we'll spend some time with what the marketing people call precision policies. I would just call it policies. This is a mechanism for distorting the response that CachEServe sends back to clients. So instead of returning what I call the natural DNS answer from a resolution, we can customize the response to suit our needs. And we'll also talk here about the rate limiting that I mentioned at this point, where we can make rate limiting very targeted against particular kinds of DNS exploits, specifically amplification attacks, for example. I mentioned that the DNS protocol is a terrific amplifier in the sense that a small request can generate a very large response, and that can be exploited by attackers for a number of purposes. So we'll talk about how policies can be used to augment the existing built-in defenses that CachEServe has, and how we can manipulate the policy to incorporate new modes of attack when those emerge. There are a couple of special topics that are of interest to only those customers who happen to be using these things. One is what's called the EDNS client subnet and associated support for what we call equivalence classes. This is a mechanism for providing an authoritative server with information about the client which has talked to CachEServe. So we'll spend just a moment looking at what that is and what the implications are. I don't think we will do the labs where you set it up, but I'll show you where they are. So if you want to introduce yourself to this particular topic and learn how CachEServe can provide this kind of feature, you can know that it exists in the manual and the training lab guide. And then there's a section on IPv6, in particular on what we call DNS 6.4. So this is a kind of a translation technology that allows a a purely IPv6 environment to interoperate with the natural internet, which has servers, websites and other internet services that may not support IPv6. And so basically an island of IPv6 network that needs to interoperate with an IPv4 world, with the legacy world. There's a way for the DNS server to cooperate with that technology by rewriting IPv4 addresses into IPv6 addresses, so that these clients can participate in DNS normally. So these are kind of advanced and top esoteric topics. If the customer is not using those, they don't really care about that. Any questions before we go on? Okay, just take attendance once more very quickly and see. I didn't mark you there. Is there? Eduardo is here. I didn't. Yeah, good. Thank you. All right. So next stop. Let's see here. This slide will look very familiar to you. It's exactly the same slide, except for replacing the word caching and CACHESERVE. I just replaced the word off-serve and authoritative DNS. So we don't need to spend any more time on this because we're dealing with the same DNS information, the same protocol as we were with the authoritative server. We're just going to be having a different location in the overall resolution chain. We already know about the different types of resource records, so there's nothing new to learn here. The resource records have maybe a little bit different emphasis when we're looking at the caching world, because things like secondary zones, slave zones, which get information about replication functionality, so the serial number and the resynchronization intervals. That information is of no use to a caching server. The only thing that the caching server will look at in the SOA record for a zone, because remember, zones are the only things that actually have SOA, is it will look at this last integer here in the SOA, which is the negative caching interval. It tells CACHESERVE how long to remember that something does not exist. And so just like with authoritative service, non-existence is a very positive result in the sense of a DNS response. It's not an answer. So if I look at dig, the answer field will show 0, no answer. However, NX domain is a very positive statement in the sense that it authoritatively says that something does not exist, and CACHESERVE will remember that something does not exist using this value here. It's sort of it's like the TTL, or the expiration date of the non-existence proof or statement. Because there is no answer, because there is no resource record with a TTL that tells CACHESERVE how long to remember that data, that information has to be transmitted some other way. And so it happens to be in the SOA, the Start of Authority record, that there is a number, an integer, that is controlled by the owner of the zone. They can indicate to caching servers how long to remember that something doesn't exist. So that's the only piece of information here that caching servers will care about. Caching servers will make a great deal of use of this name server record, however. In fact, that is the essential part of understanding or learning the delegation information from zones as CacheServe traverses the DNS hierarchy. So I guess that's the only thing that I would mention about resource records, a different emphasis on what things are important in terms of the operation of the DNS. And these NS and SOA records, those are the types that are essential for the operation of the DNS. Other types of resource records will be fetched and cached and transmitted to clients without regard to what type they are. There's no significance to that. All right, so that's more than enough on that point. We had the upside down tree. Again, we don't need to spend any more time on the concept of the nodes of the tree being labeled with text strings, like www.akamai.com is the path that leads to this particular node in what we call the DNS namespace. The fully qualified domain is that concept explains why there's a trailing dot here. The most important point for CacheServe is that it will work exclusively with domains. I mean, it will, in places where a domain is required, the semantics will dictate that you are specifying a domain. So if NOMTEL has a tab completion where you're supposed to provide a domain, or the man page says to provide a domain in the value of a field in a command channel instruction, it is this interpretation of what a domain is. It's a point in the DNS namespace, and everything below it is implied in that interpretation. As I mentioned with AuthServe, zones are a concept that only authoritative servers care about. So CacheServe is incapable of loading a zone. It has no way to publish a zone like movie.edu. So that's probably enough to say about the namespace. This picture that I stole from the Ripe guys, that remains in place. Of course, our focus now is, instead of looking at the authoritative servers, which are on the right side of the box, our focus is going to be right here in the middle, which is a very high leverage position to hold in the sense that the stub resolvers, the clients on the left-hand side, they are at the mercy of the caching server to perform this resolution in the appropriate way. So I mention that simply because with policies, we can distort the natural resolution and provide an answer which is not the natural answer from an authoritative server. So this is a very trusted position in the network. The client, unless the client is doing something like DNSSEC validation of the responses that it gets from the caching server, it doesn't have a way to confirm that it's getting the information from the appropriate servers. So this is frequently used to deploy or implement things like parental controls. When we talk about providing a mechanism for child protection, preventing access to exploitation sites or government-mandated restrictions on which web services can be resolved, the caching server is capable of keeping lists of names for which a non-natural answer can be returned to the client. So this is a very sensitive position in the overall resolving process. It's also a very vulnerable position because while the input to the server can be restricted to an operator's network, or in the case of in cell phone world, there will be just a closed network of clients that have access to the caching server. In order for the caching server to interoperate with all of the authoritative servers of the world, it has to be open to sending and receiving traffic from the entire internet. So this is exposed to a degree that typically we don't like to have our servers exposed to. Some of the kinds of threats that you get are spoofing attacks, so that answers which look like the genuine DNS response from an authoritative server, but are generated by an attacker. And so an attacker can introduce responses and try to poison the cache with bogus data in the hopes of having the web clients, or the clients in general, learn the wrong answer for some kind of say a banking website or something like that. So there's that kind of vulnerability. And there's also just more opportunities for denial of service. Of course, any internet service is susceptible to denial of service, but the variety of things that one can induce a caching server to do that will exhaust its resources. There are many variants of such attacks, including what are called random subdomain attacks, where an attacker that has access to the server as a client sends a storm of traffic for DNS names that are not expected to exist. So that's why it's called a random subdomain, because the first label is a random string, and the result of that is, well, there's many pieces of collateral damage. first, the caching server becomes overwhelmed trying to do resolution because every name is different. So nothing is in fact cached, and so there is a increase in activity to one or more of the authoritative servers. So the caching server becomes overwhelmed doing this. There's also damage on the authoritative side because the authoritative server is overwhelmed with responding to things that don't exist at all. And these are often orchestrated such that caching servers from around the world are all infected at the same time and create significant and disabling traffic on the authoritative name servers, which effectively has the consequence of bringing the website down, not because the HTTP server is overwhelmed, but because end users cannot resolve the name in order to send the traffic. So the HTTP server, the web server, becomes invisible, and so clients can't use it. So there's a great deal of problems that are difficult to handle, and the nature of the functionality in the computer science sort of philosophy of sending a request somewhere where you're not sure whether you're going to get an answer, which happens with pretty much every query that a caching server makes to an authoritative server. It has to be able to deal with the fact that the answer might come back, or it might be an answer that is spoofed, and what to do in all of those situations. So that's the situation that we have to deal with when we are a caching server. Any questions about this before I move ahead? I know this is review, but it's fun to understand why these different parts of the server will become important because of the nature of the work that it has to do. Okay, let's move ahead. That entire discussion on the previous slide was just to re-emphasize that the caching DNS has to keep track of a lot more information than, in some sense, the authoritative servers. The authoritative servers know exactly where to go to get the information that they need to produce for clients. The caching server has to not only locate those servers, but it has to then have algorithms which deal with how to obtain information from those servers. So it's a different thing. CacheServe then is a high performance caching only DNS server. Caching only meaning that there's no way to load a zone into CacheServe. I cannot put movie.edu into CacheServe. I can tell CacheServe where to find movie.edu if I have a specific name server or set of name servers that I want CacheServe to use. That's called a stub in the name of the feature, that name comes from bind. As does forward, which is another concept of telling CacheServe how to do resolution, which may differ from the standard start at the root and then follow the delegation instructions that you're sent. So you can modify that thing. So in that sense, it has the same kind of features that most caching services that you might be familiar with from other vendors. It shares those features. When I say high performance, what does that mean? It means, number one, low latency. Latency meaning the time from the client sending a request and the CacheServe receiving the request to the time when the response goes back to the client. Now, of course, the one can only guarantee to some extent the response time for information that comes from the local cache. There are mechanisms in place in CacheServe which help reduce the latency even if a resolution to the authoritative servers is required. So there are optimizations in how CacheServe determines which servers to use, which of the yellow boxes to go to when there are multiple sets of servers to use. It keeps track of the round trip time, and that concept is not unique either, but the way that CacheServe does it is it provides for low latency in high throughput conditions, and so we'll see that the maximum capacity, in other words, the number of queries per second that CacheServe can handle is optimized by the fact that this code is dedicated to caching only. And we will see that assuming some general requirements are met, such as the network is not a bottleneck, so the network is not artificially reducing the capacity or the queries per second, assuming that there's no I/O issues on the machine itself. It is the CPU which is going to dictate how many queries per second the server can handle. So the CPU will be the limiting factor in terms of what kind of computing resources are necessary in order to achieve high rates of throughput. So what is high here? I don't, we are Akamai is very reluctant to give absolute numbers, but a single machine with multiple CPUs in use, and when I say multiple, I mean between 8 and 12, we can get close to 1 million queries per second. Of course, you would not want to operate that at that level because that is pretty much saturated. When I say that's the maximum, about 1 million per second, that is the maximum, and it pretty much saturates the whole machine. So you would not operate a production environment depending on that number. You would want a lot of what they call headroom, so that the capacity can spike in the cases of problems. So instead of 1 million, you probably, as a conservative operation parameter, would probably pick something like 10% of the absolute maximum, just so that you can respond. So 100,000 queries per second is typical for what we see our operators using. And when I just mentioned here a moment ago multiple CPUs, CacheServe, unlike AuthServe, is multi-threaded, so it can take advantage of modern hardware and dedicate multiple CPUs to the very high the resource-intensive functions of the server. So we will spend some time identifying what those are and how you as an operator, how you can see where the hotspots on the server might be, and whether one can benefit from having more CPUs in use, and that's controlled by the license. The license. A minute ago, we looked at the looked at the license files on the Nominum support site. That's what the C1 and the C2, those refer to concurrency levels, and that's effectively the number of CPUs. I'm looking at the chat. Julio is asking about how do we connect on the CC, the cache serve machines. I think that's what that means, SSH, or need to download something. So let me just pause for a second here. Just share my screen here. Let me share a different screen, maybe. This one up here. So for those of you, here's where we want to go. Just sorry, pardon my interruption here. But the CachEServe is the machine that we want to be using now. Exit from mine. So you can either use the key that you already have to SSH directly to CSDNSI, and then your environment number. I think you're 12, right? Yeah, Julio's 12. You can go use that same key, or if you prefer, since you've already had established an auth-serve connection, you can just go SSH CS, just issue this command from your auth-serve instance, and then you will land on the CachEServe machine. So that's how you get to the CachEServe. Hopefully that's what you were asking about. Sorry for the interruption, but since I'm doing this introduction, now is a good time to look at the people are actually logged on. Looking to see who's logged on. We've still got two. These are the servers that I see. Students are on 2, 3, 4, 7. Those are the only ones that are logged on. So the rest of you can still do that. All right, sorry about that. All right, same consideration that we had with auth-serve, which is because the code was created from scratch. Yes, there are some concepts that are shared with Bind, for example, and other open source servers. The code is all created from scratch, Akamai proprietary, no open source code is used. Well, things like SSH, so for DNS over HTTPS, there are libraries from the open SSH that are compiled in to support the encryption regarding HTTPS kind of connections, and TLS. So yes, there are some libraries which contain a potential vulnerability that are shared. OpenSSH is the one that I can think of off the top of my head, which is fairly new because until a few years ago, there was no standard for doing DNS over encrypted channels. DNSSEC is not encrypted, remember. That uses the DNS traditional DNS with some additional resource record types and some protocol behavior changes, that is DNSSEC implements a source authentication and message integrity function. It does not encrypt the way SSH does. So that's a bit of a diversion, but otherwise this is Akamai proprietary code with the idea that we can be more efficient in the architecture because we know that we are doing caching only. We don't have to accommodate a multitude of databases and things like that. So that's and the security part of it. Part of this element originates from not using open source code, because if attackers cannot analyze the code, they can't optimize their attacks. And part of the security aspect comes from the fact that the server is very fast, and so there's a security element that is derived from the fact that we don't wait a long time for answers from slow responding servers. Yes, there's a cost to sending out additional queries sometime to authority servers, but by not waiting a long time for things, it reduces the vulnerability and reduces the sort of attack surface that is available to random brute force attacks. Now, some of you may, at some point, we may talk about you guys being in another training class with our products, which we call the SIA, the Secure Internet Access Products. I don't know if you've been introduced to any of the names yet, but there's something called ThreatAvert, which is a kind of an add-on to CachEServe, which helps protect the network and protects the DNS service overall. There is a product called SIA SMB, which is for small medium business, which provides a kind of a parental controls for small businesses. And then there's a similar product called SIA Consumer, which provides a sort of a residential equivalent, which provides this kind of parental controls and mandated restrictions and those sorts of things for your customers to prevent them from reaching websites and for providing a page that says that they cannot go to a website because of government requirements. So when or if that happens, the bottom bullet point here becomes the most important part of CachEServe. Yes, all of these things are important, but when we talk about ThreatAvert, Secure Consumer, SIA SMB, small medium business protection, those security products which prevent access to known phishing sites and botnet sites, the caching server's policy becomes the most important thing. And this is the leverage which I spoke about earlier that the caching DNS server has, because it is controlling whether a client gets the true, what I call the natural DNS answer, or it gets redirected somewhere else, because the website that the client was attempting to go to was either known to be have botnet, have infections, or be distributing malware, whether it has a known phishing site, or whether it's just undesirable for any of a number of editorial reasons, for example. So blocking child exploitation, or gambling, pornography, whatever. Just having parental controls over what kinds of services are available, during certain times of the day, certain days of the week, all of that kind of stuff. One can implement the policies in CachEServe which control whether the end user actually gets the natural DNS answer. So if and when we ever do our courses on ThreatAvert and SIA, SMB, and Secure Consumer, we will be looking at not so much CachEServe, because CachEServe actually doesn't do very much in those sequence. Yes, it's doing a lot in the sense that it is the trigger for everything that happens, and so it has to be able to recognize when it needs to intercept a request. However, after that, a lot of other things happen, and so there's a lot of a number of other components that are used to implement the parental controls. So there are other databases, there are other mechanisms in place for implementing that kind of functionality. So, but understanding how CachEServe works is a prerequisite for understanding how those other products work. Okay, that's plenty of, I think, plenty of information about that. You saw this picture before. We're just looking at a different side of the story. Where are we? Excuse me. We're looking at the left-hand side of this table as opposed to the right-hand side. So we're not going to pay any more attention to authoritative servers. Instead, we are going to be looking at the caching server, where the main function is to locate and derive responses from authoritative servers, talks to clients to get the queries. Typically, may not be a local area network, but typically in some kind of enclosed network, but talking to authorities who provide all the information that are located somewhere out on the internet. And the updates are handled by data expiring based on the TTL. So that's just a reminder of how caching is different than authoritative service. Now, here we finally get to an important diagram, which I think is a useful summary of what every caching server has to do. It is a kind of a schematic diagram, a cartoon. Some of the engineers at Akamai laugh at me when I show this picture. Oh, Spooner, that's not how it works. I know that's not how it works, but it describes a lot of useful relationships between the function, what a caching server has to do. So this box represents the process, the DNSI CachEServe process, and mapping that functionality to different elements of the configuration. So the server object will be familiar to you. The way it's configured is different. The statements for determining the listening IP addresses look different and contain different types of information. But conceptually, the server object is the configuration element that controls the overall process and how the process uses system resources, as well as the server object helps determine what network interfaces the process will receive queries from. So the server object lives sort of over here, where we have to get packets off of the wire, off of the network interface, in order for the next thing to happen, which is to validate that the query is valid, so it's formatted correctly, and that there's no policy reason that's applied to the server which prevent it from handling the query. And then you look in the cache. So just stepping through the functions after you've confirmed that yes, this query is a valid DNS query that I want to find an answer for. We look in the cache. So this is, I emphasize, in memory. So this is not on disk. This is in memory only cache of DNS data, which is initially empty. There are a couple of things in there from some configuration, but initially, let's say it is empty when CachEServe first starts up. When you start your CachEServe instance in the first exercise, the cache will be empty. There's nothing in there. And so every query, with a couple of exceptions, that is processed will be determined to need further processing from outbound, what we call lookups. So this is just the stage at which the caching server sends a DNS query to the authoritative server. So if I had room over here on the right, I could draw the yellow boxes. This is where CachEServe is sending DNS queries. They're regular old DNS queries. They go to port 53. They have all the same look and feel of a normal DNS query. There are some details about the flags that are set. For example, CachEServe will send DNS queries that have a no recursion flag. So there's a bit set in the outbound packets. Again, I don't want to get too deep into this, but there is a bit for recursion desired. That bit will not be set. It will say it's a way of CachEServe saying to whoever receives this query that if you don't know the answer, don't go looking anywhere else to find it. Just tell me that you don't know the answer, and then any other information that you might have. So for that reason, I don't call these outbound queries. I could say that there are inbound queries from the clients on the left-hand side, and there are outbound queries to authorities on the right-hand side. But in order to help distinguish these two different, the different underlying motivations for the query to exist at all, we call these lookups. So in the statistics and other places in CachEserve, you will see the word a lookup. So it's used a few times. We can do lookups in the cache, and we can do lookups to authoritative servers. But in this outbound lookup processing, all I'm saying is that there are this represents all the activity for sending requests and receiving responses from authorities. So this picture is very useful to keep in mind as we go through the different labs and look at what the view selectors, the views, and the resolvers are doing, how the server overall is using resources, and how to interpret statistics in terms of information about the cache, not only its size, which in general will be maximized very quickly. In a production environment, this cache will fill up within seconds with data. And by definition, it will be the most popular data because that's what's going to survive in here. We can look into this cache. So there are command channel instructions that we can use to go in to the cache and locate the information about DNS names that CachEserve has collected. We can look at the size of the cache. We can control the size of the cache. There are other diagnostics around different statistics for how many queries are outbound, how many queries are inbound, all of this kind of stuff. So keeping in mind this picture, which is just a simple schematic, but nonetheless, remember this is how a caching server will work. Any questions about that before I move on? Okay. The command channel, so here's CachEserve's command channel, runs on a different port than AuthServe's command channel, but otherwise it is identical. So everything you know about command channels, about how you can create alternative command channels, you can make command channels listen on different addresses, what processes, what elements, what components will talk to CachEserve over a command channel. All of those things are exactly the same. No differences. The tool that you use, NomTel, to send these command channel instructions, exactly the same. Everything the same here. The SDK, exactly the same. I'll take advantage of some extra time to look at scripts that we can write using the SDK. There is a database. So CachEserve has a database. However, its job is not to store resource records, which is the case with CachEserve, sorry, with AuthServe. Authoritative servers have zones that are stored in the content databases. But CachEserve does have a configuration database. So there is a database which is a VDB2 database. It's a proprietary format. Say a little bit more about that later on. So when CachEserve is running, one accesses that database through the command channel. When CachEserve is not running, there are utilities, just like there was with ANSP dump configuration and ANSP edit configuration. There are tools analogous for those needs. You know that by default, the command channel is listening only on the loopback address. but you can change that by modifying the channel.conf file. There was the exercise, we skipped it at the end of the lab with authserve, but that gives you exact instructions about how to change the port number and the socket. There is a command channel secret, which is generated randomly at installation. Change it if you want. Nothing new, same situation as with authserve. As with authserve, I want to just make a contrast or a comparison to similar what an open source product like Bind or named, as the process is known, might use. And I showed this picture here with authserve, where the text file configuration had global statements and then maybe had some view specific statements that controlled the specifics of how resolution would take place. We would not have zones here, but we would have instructions for forwarding, for root hints, for stubs, for other features that determine the behavior of the resolution process. So CachEserve, like authserve, does not have a main configuration file. It has instead a configuration database, which I mentioned a little while ago. Is the second generation of the VDB proprietary database architecture. This is a multi-threaded database. That's where the version 2 comes from. So you'll see the files, the journal files, look a little bit different than what you saw with the authserve's legacy VDB single-threaded database. But every CachEserve will have this VDB database, which is used exclusively for configuration. That's the only thing that's in there. When CachEserve is running, you use nomtel to access the configuration, and then CachEserve is the client to the database, and CachEserve then makes the changes in memory and writes the journals to disk. There are checkpoints, just like there are with authserve. So the maintenance is exactly the same. The files don't have the same names, a little bit different feel. And one last remark is that the cache is never written to disk at all. So there is no in the CachEserve's database. You might think that, well, there's a copy of the cache in there, but there is not. There at no point does the CachEserve ever write that DNS data that it's seeking and serving. That information is never written to the disk, and it's not possible. There is no tool that will allow you to write the cache to disk. However, with nomtel, you can look at the contents of the cache. They're constantly changing, of course, but at any time you can look into the cache using command channel instructions, and you can read the data, you can manipulate the data. There are configurations that essentially allow you to put permanent entries into the cache. So you can write to the cache. That's something we call a preload, and I'll have you create a preload in the first lab. That is a persistent entry in the cache. So in that sense, for specific entries, okay, you could say that those entries, because they're part of the overall configuration, those are persistent on disk and on the database. But otherwise, the DNS data, the cache, the live cache information is never written to the disk at all, and it's not possible to do that. Okay, let's see what else we got. Summary of the features: multi-threaded, unlike auth-serve. Talked about looking into the cache. Talked about shared cache. This will what I mean by a shared cache will become more clear later on. For now, it's sufficient to know that the cache is part of the resolver object. We'll spend a lot of time after our break when we talk about the resolver object. It's the critical element in the CACHESERVE configuration. Much like a zone is the critical object in an auth-serve configuration, I would say the resolver is the analog to that. The good news is that unlike with the zone, where we had to deal with a lot of the machinery of databases in order to optimize the resources so that the zones were using the databases properly. The resolver is relatively simple. It's certainly in terms of the underlying machinery, the activity and the potential for I won't say for vulnerabilities, but the potential for just multiple paths of behavior is greatly increased on a resolver, because the resolver has to make a lot of decisions about which authoritative servers to talk to get those answers. We already mentioned the precision policies. Again, I just call these policies. This is a marketing term, is precision policies, but policies. One of the uses of policies is to say deny service completely. So that's the example that we will use. I talked about amplification attacks against the DNS, policies that will rearrange the addresses and suppress some addresses if you want. So there's some policies that can do that. What we call the layered resistance to vulnerabilities in the DNS. I will talk about patented structure of the cache that we call glue segregation. This is a way of separating delegation information from DNS data that is authoritative in the sense that it comes from the owner of the zone. So this we'll talk about later. We'll see that CACHESERVE is what you might look at the surface appears to be somewhat wasteful in the sense that it throws away some information that it could use. It's conservative about what it remembers when it gets a referral. The benefit of that is that there's a more secure approach to doing resolution. The disadvantage is that it costs more time and it costs more resources, computing resources, in order to look up some things. But the overall philosophy is that because we've optimized all of these other areas for the 99.99% of the time when the normal path of resolution is followed, that we can afford to be a little bit conservative and afford to throw out some things that other vendors might keep in their cache, because it will not impact the performance as much on average. And this spoofing defense will talk about how CachEServe can reduce the likelihood that spoofing is successful. There are statistics. We've already talked about the query store, SNMP agent. All of that stuff is exactly the same, so I'm not saying anything new here. I will say the DNSSEC support. Remember I talked about signing zones yesterday when we looked at AuthServe. DNSSEC is trivial to enable in AuthServe. There are basically two configurations, one that make CachEServe DNSSEC aware, and then there's a second that actually causes it to do DNSSEC validation. Although it's trivial to enable, it does introduce performance concerns because the cache will grow bigger, faster. The amount of traffic that will be created will increase significantly. The computing resources necessary to do cryptography will increase, and troubleshooting becomes much more difficult. The potential for if there is a problem with a signed zone somewhere, and that, say, a key roll did not go well, or signatures were not replaced in a timely way, that will lead to serve fail responses being sent back to clients, and the customers will blame the operator of the caching server for the problem, even if the problem resides on the authoritative side. Customers are not going to say, "Oh, it's the problem of Microsoft or Google." Even if it was Microsoft's or Google's name server's problem, they will blame the carrier who is providing the caching service, because that's why they can't get to the website, because the DNS is failing because of DNSSEC. So while the bottom line is that while it's trivial to enable in CachEServe, the decision to do so is not one that operators will take lightly. Okay, so I think we've looked at everything that we want to do for an introduction. Here I just mentioned, and you saw this earlier when I looked at the Nominum support site. The product was called Vantio once upon a time when the caching name server, which originally, by the way, was called CNS, very unimaginatively, much like ANS for the authoritative name server. There was a product called CNS, or caching name server, which then later the brand name, the name of the product became Vantio. So that was the single-threaded version of CachEServe, was Vantio. And for a while, Vantio, we kept the name when the new multi-threaded CachEServe 7 was introduced. That product was called in the Nominum days up until 2017 or 18. It was called Vantio CachEServe. Now Akamai calls it DNSI CacheServe. So you may see this word Vantio hanging around in some places. Okay. Are there any questions? I think we could, we're in a good spot to take a short 10-minute break.